So I'll keep blabbing. Okay, so we're recording. Okay, people that are still trying to add, you're waiting to add. Some of you turned in the homework, some of you didn't. So if you did not turn in the homework, you're lower in priority already. Okay, and keep doing that. I won't add anybody to the class today. I want to see how trustworthy you are for the next time. Okay, so however far I get in class today also, then you submit the homework for next Tuesday also, okay? And then maybe I'll start adding people on Tuesday. All right, so I was already done with 12.1. Okay, now let me change this already. I totally goofed over here. As you can see, exam 2, okay? So that kind of makes up a day right there. So that being the case, see where it says exam 1, Tuesday 2. I'm going to slow that down. Let's make it 2-4 now. So February the 4th is exam 1. So everybody please make a note of that change. I will raise it up again because raising it up makes it easier to see. Again, if you say, how come you don't do that all the time? I'm literally raising it up. My document camera doesn't have a focus option, so this is all I can do, sorry. Okay, so let's make our first exam for now, Thursday, February the 4th. So I don't have to rush through all of this stuff over here. Okay. All right, so my goal is 12.2 and some of 12.3, and then we will have a quiz at the end. And that's that. Again, those of you that are trying to add, still, if you want higher chance of adding, do the homework. Everybody else that's already enrolled, you don't have to do that. Okay, you just submit the homework along with the exams. Okay, so I am done with this. So I'm going to start 12.2 and some of 12.3. Okay. So again, please make a note, moving the exam back to Thursday 2-4. This is totally all messed up now. So I'll just probably push some of these days back. And maybe that's enough to, move this exam to 5/13, then we can have a day for review. But we'll see how it goes. Okay. All right, so I'm going to get started with 12.2. Here are the problems. Okay, and let me get the book and show you stuff. And I think I did some of this last time, but I'll do it again. In case you say, I don't want to buy the book, I'm never going to get the book, I will just show you all the key pages. Okay, so page 798, vectors. Okay, so we talked about this last time, hopefully. You have an initial point and a terminal point. It says there, sorry, I can't point it out to you because I'm using both hands to lift up the book. Okay, and we talked about this. So you combine the head of one with the tail of the other, so you can see u plus v. You also see v plus u over here, so that's the same thing. And then scalar multiplication, page 799. Okay, a scalar is just a number. So see CV. Okay, and I'll give you my convention. Okay, now the author, Mr. Stewart. So if you hear me say Mr. Stewart, it's the author. Okay, so he uses bold print for vectors. So you see the A and the B, and see over here where it says CV. This is kind of hard for me to do, but right here, right? CV. C is not bold, it's regular type, but V is bold. So he uses bold for vectors and non-bold regular print for scalars. What am I going to do for vectors? I'll put a little arrow at the top. Okay, so this is the way I'm going to write vectors, and you can do likewise. Some people use an exact arrow. It takes a little bit longer to draw a full arrow, right? You can't draw a full arrow without lifting up your pencil from the paper, right? So I just kind of go like that. And you can do likewise for a vector, okay? Because I don't have the time or energy to make them bold, right? Now, of course, the author can make it bold, make it look nice and pretty, and charge us lots of money to buy the book, right? So that's a vector, that's a vector. For me, for a vector, I'll just put an arrow on top. So Mr. Stewart has it bold. This is my vector U, vector V, vector W, okay? And you can do likewise. Don't do the bold stuff. Okay, so scalar multiplication, a number times the vector. So we talked about this last time. Here's vector V, 2V. Double the magnitude, same direction. negative v, opposite direction, negative 1.5 v, and so on. Okay, and here's a definition of u minus v, u plus negative v. That's just like it was for real numbers, right? A definition of a minus b is a plus negative b also. So that kind of looks like that. Okay, we will be breaking up vectors into their components, x and y, or x, y, and z components, depending if you're in 2 dimensions or 3 dimensions. Okay, so here's a 2-dimensional vector, a1, a2. So here's a vector a. There's a horizontal component, or you can say x component, and a vertical component, y component. 3 space, okay, a1, a2, a3. So here's the vector a. It has an x component, y component, and a z component. Okay? And of course, I already told you last time, I'm not going to draw it like this, and I don't want you to draw it like this either. Okay? I want you to draw y and z just like we used to have x and y, and the only oddball out is x. Okay, said that before. So Mr. Stewart does it his way. I want you to do it my way. Okay? Y and z are just like the x and y before. That makes sense, right? And x is like that. You pretend x is coming out of the page. Okay, if you're given 2 points, either 2D or 3D, okay. And by the way, it should be obvious whether you're 2 dimensions or 3 dimensions by how many components you have, right? So if I just show you A1, A2, you know that's 2-dimensional. If you see A1, A2, A3, you know that's 3-dimensional. Sorry if I'm shaking because it's hard to hold the book when it's so heavy and all that. All right, so you're going from one point to another point. How do you find the vector? You know, just subtract the components, right? So here's the 3D version. If you're going from x1, y1, z1 to x2, y2, z2, just subtract. x2 minus x1, y2 minus y1, z2 minus z1. Okay. Do you have to put that in your formula sheet? I don't think you need to, right? Okay. Another way you can think of it that's less writing is delta x, delta y, delta z, right? What's the change in x? What's the change in y? What's the change in z? Okay, and the other thing we want to mention from this picture is vectors are considered equal if they have the same magnitude and same direction. Okay, so in this picture, figure 12, all of these vectors are the same. Okay, they call it the vector A, which is 3, 2. That's 3 in the horizontal direction, 2 in the vertical direction, right? So start anywhere, 3 to the right, 2 up, it's like that. So all of these are considered equal vectors. So vector doesn't necessarily have to be in any one position. Okay, so if 2 vectors have the same magnitude, same direction, they're considered equal. Okay. All right. Magnitude or length of the vector. Okay. How do we write it? Okay. Well, you can either write it like this or like this. Okay. Double bars. Okay. I guess ideally it should be double bars. You can see there's a problem with a single bar, right? Can you guess what's wrong with a single bar? We already have a meaning for that in mathematics, right? Absolute value. Okay. Now, if you see a vector inside, you say, well, we're doing a vector. We know we're not doing absolute value. So that's correct. Okay, I mean, the context is clear. So if I draw the bars and I put -3, then you know, okay, I'm doing absolute value of -3. But if I put inside a vector and I put the bars, then okay, I'm not doing absolute value. I'm doing magnitude or length or norm. You will also hear me say norm, N-O-R-M. Okay, that also means magnitude. Okay, and it's really just a Pythagorean theorem. So what's the length of the vector, right? Square root of a1 squared plus a2 squared, 3D at a3 squared. Okay. So again, I asked you, do you want to put that in your cheat sheet or not? Your choice. If you think that's pretty easy to memorize, don't put it. Okay, remember you get one 8.5 by 11 sheet, double-sided. Okay, but if you put too much, then you might not have enough room for other stuff, right? All right, so this is basically just Pythagorean theorem when you stop and think about it, right? How do you find out how long this vector is? Pythagorean theorem, right? Square root of this thing squared plus this thing squared, right? So in this case, square root of 9 plus 4, square root of 13. Is that right? Okay. Okay, properties of vectors, page 802. Most of these are very obvious. So do you have to memorize it? Well, sort of, but you kind of know them already. I mean, that looks like the commutative property. That looks like the identity property. And please notice, this is actually the zero vector. Okay, see how it's bold? Okay, so bold is a zero vector. What is the zero vector? It's a vector with a magnitude of 0. And if you stop and think about it, if you have a magnitude of 0, you can have any direction. Okay, think of a beacon of light, like a lighthouse, right, that just turns. If it turns, it's still there, right? The magnitude is 0. So even as it changes directions, you're still at the same place. Okay, so the 0 vector has magnitude 0, but any direction that you want. So you can just gloss over that. I wouldn't stress over it. Most of these are very obvious, like that one. You kind of know that from algebra. Same for that. That looks like the associative law and so on. Okay. All right. Special vectors. I, J, and K. Okay. I is 1 unit in the x direction. J is 1 unit in the y direction. So if you're in 2 dimensions, here's I and J. Right? 1 unit to the right, 1 unit up. In 3 dimensions, I is still 1 unit in the x direction, but we know x is coming out of the paper. J is 1 unit in the y direction, except we know that y is going to the right. And K is 1 unit up. I, J, K. Now, come on, you don't really need to put that on your formula sheet, right? I, J, K. It's alphabetical. So if you ever forget, oh, which one's I, which one's J, which one's K? Well, you know the alphabet, I, J, K, X, Y, Z, right? X, Y, Z. So here are the vectors I, J, and K. And again, I don't want you to write it like this. I've told you the way that I want it. Okay. Well, again, please notice this is a special view. This is the first octant view that I talked about, right? Where you don't draw the whole thing, you just draw the first octant. Okay? Just like the first quadrant view in 2D. This is the first octant view, O-C-T-A-N-T, octant. There are 8 octants. Get my Rubik's Cube here again, right? There are 8 octants, 1, 2, 3, 4 in the top, 1, 2, 3, 4 in the bottom. Okay. Imagine the origin is in the middle of this Rubik's Cube, right? And then you have your 8 corners representing the 8 octants. Okay. So I is 1 unit in the x direction, whether it's 2 or 3D. J is 1 unit in the y direction, 2 or 3D. And K has to be 3D, 1 unit up. Okay. So I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. It's an ordered triple, right? X component, Y component, Z component. Okay. So that's that. I think we can get started. So the assignment is what again? 12.2, 3, 5, and 9 to 35 odd. Okay. Again, I'll do a bunch. Okay. And I aim to show you some of 12.3, and then we'll also have a quiz. All right. So that's the game plan for now. And let me show you some stuff. Okay. So for those of you that don't want to get the book, so 12.2, where am I? Page 805 for the benefit of those of you who want that. Okay, so I'm trying to aim it so you can see it. 4 and 5, 6 and 7. Okay. And I know I'm going fast, but you know, this is on the video, so you can always pause the video, fast forward, rewind as much as you want. 15 through 22. And that. And that. Okay, how far do we have to go? 35. So a few on the next page. Okay, here we go. Yeah, stuff like 32 and 33, you physics people have probably seen that before, right? And 35, so there's 35. And there we go. And I got to put the book down because the book's too heavy. All right. Okay, problem number 3. Name all of the equal vectors in the parallelogram shown. Okay, equal vectors, same magnitude, same direction. Okay. So here's the picture. All right. So DA and CB are equal vectors, right? Okay, so again, the way I'm going to write the vector is with a little arrow like that. And by the way, this is the convention that it's always going like that. So it doesn't mean the vector has to move exactly to the right. The vector can move to the left or up or down or sideways or whatever, but we write it this way. Again, Mr. Stewart will have it bold. So DA and CB. What other vectors are equal? Looks like A, B, and DC are equal. So the vector AB and the vector DC are equal. And then how about these? Let's see. DE and EB. So the vector DE and the vector EB are equal. And by the way, these are directional. I think you can see the vector EB is not the same as the vector BE because that'd be going in the other direction. Right? So the letters do matter. Then how about going this way, right? So how about CE, the vector CE is equal to the vector EA. So there we go. Okay. Number 5, well, all we can do is kind of trace it. So we're just giving it the old college try, as it were. So your picture may not be exactly the same as mine. You know, it depends how well how accurately you draw that and that and that. Okay. So they want you to combine all these vectors. So you just join the head of one to the tail of the other. Okay. So number 5, I'll show you some of those, maybe not all of them. So I try to copy, that's U, that's V, that's W. At least you get the idea. Okay, so for A, they want U plus V. So I write vector U, and I join the head of one to the tail of the other. So U, V, like that. So it lands here. So you would have gotten the same location as if I went straight from there to there. So in red, this is the vector U plus V. Okay, so there's U. I just copy that. There's V. There it is. So there's U plus V. Okay, letter D asks for U minus V, which by definition is U plus negative V. Okay, so what is negative V? It has the same magnitude, but the opposite direction. One way to think of it is leave that alone and just kind of move this tip so that it looks this way. Right? So negative V looks like that, right? So U minus V is U plus negative V. So here's U, here's negative V. So now U minus V is going like that. Okay, that's all. And then E asks for V plus U plus W. Join V plus U plus W. Okay, so I try to trace V, U, and W. Okay, so V is going like that. Okay, by the way, if you have to do this for me on the homework or quiz or test, don't worry. I'm not going to measure it and say, oh, you're off by 1 millimeter or whatever. If you get pretty close to it, that's okay by me. Okay, so here's the vector U. V. Then they want you to add U. So U goes directly to the right. And then W kind of goes a little bit to the left and down. So V plus U plus W. So this is the resultant vector. Sometimes it's called the resultant, R-E-S-U-L-T-A-N-T. Okay. Or think of, how do you spell resultant? Put result ant. Like you have a tiny little ant crawling across the street, right? So result ant, resultant. So here's the vector V plus U plus W. Okay, that's all. So hopefully no big deal. Okay, yes, I know some of you put something in the chat. I'll get to that eventually. Okay, 9. Find a vector A with representation given by the directed line segment AB. Okay. Oh, look, Mr. Stewart even puts the arrow thing above. Okay, so you're going from A to B. What's the vector? So it's just delta X and delta Y. Okay. And by the way, just quickly look at, say, 9 and 13 there. Sorry, I can't show it to you, or maybe I can show it to you quickly. 9 and 13. It should not be a mystery. You shouldn't have to say, I wonder if this is 2-dimensional or 3-dimensional. Is it obvious? Right? Like number 9, 2-dimensional. 13, 3-dimensional. There's 3 numbers there, right? So you know whether it's 2D or 3D. Okay. So number 9, A is -2, 1, B is 1, 2. So if I'm going from A to B, what's the vector AB? Well, delta x, delta y. So it's x2 minus x1, 1 minus a negative 2, comma, y2 minus y1, i.e. delta y, 2 minus 1. So the vector is 3, 1. Okay. Quick double check. If you go from negative 2 to 1, isn't that a delta x of 3? Right? And if you go from 1 to 2, that's a delta y of 1. Okay. And in directions, it says, draw that vector and then draw the equivalent representation starting at the origin. Okay, so no big deal. All you basically do is plot the 2 points. Okay, so here's negative 2, 1. Here's 1, 2. There's the vector AB. And then they say show the same thing but emanating from the origin. So there it is. And then from here I go to 3, 1, 1, 2, 3, 1. So that's that. Okay. And then 13 is 3-dimensional. So A, 0, 3, 1, 2, 3, negative 1. Okay. Of course, the graph's a little bit harder in 3D. So I want you to try it. Okay. So you're going 3, 0, 1. Oh, sorry, doing the wrong one. 0, 3, 1 to 2, 3, negative 1. So what's the vector AB? Okay. So I just subtract. 2 minus 0 is 2. 3 minus 3 is nothing. Negative 1 minus 1 is negative 2. So the vector AB is 2, 0, negative 2. Delta x, delta y, delta z. Double check. If you start at 0 and you add 2, your delta x is 2, then you're at 2. You start with a y value of 3, you end up at 3. So delta y is 0. You don't change y. Okay. And for z, you start at 1, you end up at negative 1, so you drop 2. 2, 0, negative 2. Now, graphing it's a little bit tricky. Okay. 0, 3, 1 is actually fairly easy to graph because x is 0. That means you're not going out of the plane, you're not going into the plane. So you're just doing y as 3, z as 1. It's just like the xy plane used to be. So I go 1, 2, 3 to the right and 1 up. Okay, so there's the point A. Point B is a little bit tricky. Okay, now I put it here. That's supposed to be 2 out, 3 right, and 1 down. And yeah, you kind of have to use your imagination that that's the point. 2, 3, negative 1. Okay, so I just draw an arrow like so, and that's it. Okay, and if you're anywhere in the ballpark, I'll give it to you. Now, draw the same thing emanating from the origin. That's actually a little bit easier. Okay, so 2 in the x direction, that's 2 units out. So I'm over here. Y is 0. That means I'm not going anywhere to the left or to the right. And I go 2 down, so I drop 2. So I'm going to imagine this is the point. So this is the corresponding vector. Yes, I know sometimes it's difficult to see that. This you should be able to see, right? 2D, we got no problems, right? We're drawing 2 dimensions. My paper is 2 dimensions, okay? But here we have to create the illusion of 3 space, right? I'm trying to draw a 3-dimensional object on a 2-dimensional paper, right? But that's supposed to be the vector there. Okay. Okay, 17. Find the sum of the given vectors and illustrate geometrically. It is real easy to add vectors like this. Okay. Can you guess how you would add these? Just add x with x, y with y, z with z. What can be easier, right? So 301 plus 080. 3 plus 0 is 3. 0 plus 8 is 8. 1 plus 0 is 1. Okay. The hard part is to try to illustrate that geometrically. Okay, so here's my attempt at it. Okay, since everything here is either positive or 0, I did a first octant view, right? The book does a lot of first octant views. That's like first quadrant in 2D. right? In 3D, first octant, O-C-T-A-N-T. Okay, here's what I'm going to try as 3, 0, 1. So it's 3 out. So here I'm pretending I'm walking out 3 units. Y is 0, so I don't go anywhere left or right. And 1 unit up. So there's my illustration of 1 unit up. I land over here. Now I add 0, 8, 0. Okay? Or using IJK, it's 8J. That's just 8 units to the right. So I go 8 to the right. And here's another tricky thing. Okay, I drew 1, 2, 3, 4, 5, 6, 7, 8. But because this first vector is here, I don't draw it out to here. Okay, I'm only drawing out to here where you have to imagine that this is parallel to this. Okay, so that you have to make the illusion that you're looking at an angle. You guys know what I'm talking about? So even though this is 8, now in 2D, you say, oh, it's 8, I'm just going to go straight down. Not here. Okay, here I'm creating the illusion that I'm going straight up here. So I'm going to say that this is 8, where this kind of matches something like that. All right, so when I add these two, there's my corresponding vector. Okay, 3, 8, 1. So there's 3, 8, 1. Yeah, let me raise it up again for better. Yeah, you're probably saying, wow, this is a lot better view. Why don't you keep it all the time? I can't because I'm lifting up the paper or the book. Okay, so sorry about that. Okay, but 3, 8, 1, whoops. That's 3 out, 3 out of the paper, 8 to the right, and 1 unit up. That's supposed to be illustrated right over here. Okay. All right, then let's see. Show you something like 21 maybe. Okay. So vectors I, J, and K. Okay. So you can write I, J, and K, but it's the same thing if you just write 4, negative 3, 2. Now this one has no J component, so this one would be in braces 2, 0, negative 4. Right? I'm going to prefer to use the brace notation as much as possible. It's less writing. Okay, but I'm going to keep writing I, J, and K enough that you kind of get used to it still. Okay, so 4I means 4 in the X direction. Negative 3J means negative 3 in the Y direction. And 2K is 2 up. Okay, you can write it like this. I'm going to do this more often than this. It's easier, but they mean the same thing. Okay, A plus B, 4A plus 2B, and all this stuff. Okay, so 19 and 21. I will show you 21 because it's 3-dimensional. You should be able to do the 2-dimensional version. Yeah, and just to bring home the point, for problem number 21, I even change it up. So the book says 4I minus 3J plus 2K. Again, to write a vector, I draw an arrow. I don't even draw the whole arrow because I'm too lazy to pick up my pencil and draw that bottom part, right? So I just flick it up like that. This is the same as 4, negative 3, 2. So again, I will write this more often than this. Here you do have to be a little bit careful though. So 2I, which is a positive 2I, minus 4K, there's no J component, so you pretend it's 0. So this is 2, 0, negative 4. So A plus B, just add them up. Add the I with the I, J with the J, K with the K. So 4 plus 2 is 6. That's a 6 there. Sorry, I wrote it funny. That's SIX, 6. Negative 3 plus 0 is negative 3. 2 minus 4 is negative 2. That's real easy, right? Or if you want to write it in IJK, that's a 6. 6I minus 3J minus 2K. Then it also asks for 4A plus 2B. So this is scalar multiplication. In scalar, S-C-A-L-A-R, don't get scared. Scalar just means a number. So why don't they just say number? Well, usually when you're talking about vectors, the opposite, so to speak, or contrast of a vector is a scalar. So it's a number. So 4 is considered a number or scalar. A is the vector. So 4A plus 2B. So how do I do that? 4 times, here's the vector A, plus 2 times, here's the vector B. So 4 times this vector. 4 times 4 is 16. 4 times -3 is -12, right? Real easy. 4 times 2 is 8. And then 2 times this vector is 4, 0, -8. And then just add the vectors. So 16 plus 4 is 20. -12 plus nothing is -12. 8 minus 8 is 0. Okay, that's a 20. That's a 20. I messed up. Sorry. I'll raise it up for a little while. Okay, sorry, I can't keep it up there that long. I know it kind of makes it feel like you're at the eye doctor. Okay, and using IJK notation, 20, that's a 20I minus 12J. Okay, there's one nice advantage of doing IJK is that if any component is 0, you can just leave it out, right? So there's no K, so you can just put 20I minus 12J, right? So that's a little bit easier. Okay, they asked for this. It looks like absolute value, but it's not. For a vector, it means the magnitude of the vector. Okay. What's the length of the vector? Length, magnitude, norm, all the same thing. Okay. It's basically Pythagorean theorem. Great big square root of this squared plus this squared plus this squared, right? Do you want to put it on your formula sheet? Totally up to you. So here we go. Okay. Or maybe I would suggest to you, if you're going to put one down, only put the 3-dimensional flavor down. Because if you have the 3-dimensional one, right, you certainly will get the 2-dimensional one. Just make the 3rd dimension 0. So square root of a1 squared plus a2 squared plus a3 squared. So magnitude of vector A, square root. 4 squared is 16, -3 squared is 9, 2 squared is 4, radical 29. Okay, they want the magnitude of A minus B. Okay. So what's the magnitude of A minus B? I'll show you what they have in the text. Okay, sorry, I can't. Okay, so see problem 19, and above it at the very end, magnitude of A minus B. Sorry, the book's heavy. So first figure out A minus B. So here's A, 4, -3, 2. Subtract B, 2, 0, -4. So 4 minus 2 is 2. -3 minus nothing is -3. 2 minus a minus 4 is 6. And I'm only willing to raise it up just for a short while. Sorry. Okay, do the same thing. All right. Does this mean absolute value of A minus B? No, there's vectors in there. So it's a magnitude. So square root of this thing squared plus this thing squared plus this thing squared. So square root, 2 squared is 4, -3 squared is 9, 6 squared is 36, 4 plus 9 plus 36 is 49, square root of 49, 7. Okay. Okay, a new concept. Hopefully it's not too bad. Unit vector. 23, 24, 25. Unit vector. A unit vector has a magnitude of 1. Okay. So you can put that down if you want. You probably have it in the text somewhere. Yeah. Unit vector, it's on page 803. A unit vector is a vector whose length is 1. Examples are I, J, and K. Negative I, negative J, and negative K also are unit vectors. Their magnitudes are 1. How do you get a unit vector in the same direction as the original? Okay, so suppose I have a vector. Okay, I got a vector. Its magnitude is 7. How do we get a unit vector in the same direction? I just divide by 7, right? If the length is 1,000,000, I'll just take the vector and divide it by 1,000,000, and then the magnitude is 1, right? So to get a unit vector, take the vector and divide it by its magnitude. Okay. So U, which from time to time will stand for a unit vector is A divided by magnitude of A. So just take the vector divided by its magnitude, you have a unit vector. In this class, we will quite often need to have a unit vector, a vector of a length of 1. So just take the vector and divide it by its magnitude. That's all. Okay. Again, it's up to you. Do you want to put it on your formula sheet or not? Okay, so 23 and 25 are like that. I'll do the three-dimensional flavor, 25, and you do 23. Find a unit vector that has the same direction as a given vector. So just take that vector and divide it by its magnitude. 8, -1, 4. 8i minus j plus 4k. Okay. So what's the magnitude of that vector? So magnitude, not absolute value. You can tell, right? If I just have a single number here like -37, then you say, oh, it means absolute value of -37. But when I write that, or if I write 8i minus j plus 4k, it's obvious it's a vector, not absolute value. So square root of 8 squared is 64, -1 squared is 1, 4 squared is 16, 64 plus 1 plus 16 is 81, square root of 81 is 9. So to get a unit vector in the same direction, just divide by 9. So 8 over 9, -1 over 9, 4 over 9. Or using ijk, 8/9 I minus 1/9 j plus 4/9 k. Right? So this is a unit vector in the same direction as the original. Its magnitude is 1. Because this vector has a magnitude of 9. So just divide by 9, and now this is a unit vector, vector of magnitude 1.
Will you be looking for us to convert it back to IJK?
Do I have to convert it back to IJK? No. In general, you don't have to. Okay. Unless I say otherwise. But yeah, I guess the original problem had IJK, right? So yeah, I guess it would be natural to do that. But I'm generally not going to take off points for that. Okay, you can just leave it like this in general. Okay, a few more problems. I'm almost done. I know some of you had something in the chat. I'll get to it. Some word problems. 29. The vector v lies in the first quadrant and makes an angle of pi/3 with the positive x-axis, and the norm magnitude of v is 4. Find v in component form. Okay, pi/3 or 60 degrees. Okay, so here's the picture. The magnitude of v is 4. You can't see that. Yeah, now maybe you can see it. Sorry, if I lift it up, the paper is going to curl also. This is a challenge. Magnitude of v is 4, and the angle is pi/3. All right, so you know from trigonometry, the cosine of pi/3 is the x component divided by a hypotenuse. Okay, so the x component is 4 cosine pi/3. And likewise, the y component, well, the sine of pi/3 is opposite over hypotenuse. Okay, so that means the y component will be the hypotenuse times the sine of pi/3. So the vector v in component form is 4 cosine pi/3, 4 sine pi/3. Okay, and a little bit of trig. Cosine of 60 degrees is a half. Sine of 60 degrees is radical 3 over 2. So clean it up, 2 comma 2 radical 3. So this is almost just like a trig problem, folks. So another way of saying it, if you have this picture, you have an angle of 60 degrees, pi/3, and this is 4, then the x component in the x direction, it's 2 units, and up is 2 radical 3. Okay. So that's all for that one. Okay, and then what time is it? It's not even 7 o'clock yet, so I think we're good. 33. And then that's pretty much the last one that I had. 33, find the magnitude of the resultant force. There's that word resultant. Okay. It's like the result. And the angle it makes with a positive x-axis. Okay, so 33. To the left, you've got 300 N, which stands for newtons. That's a unit of force. And then you have 200 newtons going up at 60 degrees. And you physics people have had stuff like that too. Or imagine 2 people are pulling at this rope, right? One person's pulling like that, the other's pulling like that. What's the resultant? Okay, which way is the object going to go. So we're going to break it into their X and Y components. All right. So, boy, this book is heavy. Okay. So here we go. 300 newtons, 200 newtons, 60 degrees. Okay. Now, this is negative 300. It's going to the left. Okay. So I want to find the X component and the Y component. By the way, the Y component of the resultant is easy. This vector has no Y component, right? So the Y component is just this. So that's going to be 200 sine of 60 degrees. That's basically it, right? Again, this Y value, the sine of 60 degrees is Y divided by hypotenuse. Okay. Do a little bit of algebra. So Y is equal to hypotenuse times the sine of 60 degrees. Okay. There are two contributing factors to the X component, right? You've got the negative 300 going to the left, and then this positive direction component is 200 cosine 60 degrees, right? And then just combine it. Okay. So this comes out to be negative 200. Cosine of 60 degrees is a half. Half of 200 is 100. Negative 300 plus 100 is negative 200. And then, let's see, sine of 60 degrees is radical 3 over 2, multiplied by 200, 100 radical 3. Okay, so here's the vector in component form. Now it asks for the magnitude and direction. Okay, so the vector looks like this now. This is negative 200. This is 100 radical 3. Let me try to raise it up. So we know this is the components, or negative 200i plus 100 radical 3j, like that. Okay, so they're asking for the magnitude and the direction in standard form. Okay, so a little bit of trig also. This one's just Pythagorean theorem, right? So what's the magnitude of the resultant? Well, it's a squared plus b squared equals c squared. Okay, so it's going to be negative 200 squared, 40,000, plus 100 radical 3 squared, 30,000. So 40,000 plus 30,000 is 70,000. 70,000 is 7 times 10,000. That way I can take out the 10,000 as 100, right? Square root of 10,000 is 100. So 100 radical 7, 264.6 newtons. Right, so if one person's pulling like this at 300 newtons, the other person's pulling like this at 200 newtons, the net result is going like that, 264.6 newtons. Okay, and how do I find the angle in standard position? A little bit of trig. Okay, I temporarily call this angle alpha. I call this alpha because I want this to be theta. Okay, so from trig, the tangent of alpha as positive numbers now, okay, I don't have to deal with negatives. Okay, just pretend you have this triangle. Tangent is opposite over adjacent. So 100 radical 3 divided by 200, that's radical 3 over 2. So tangent of alpha is radical 3 over 2. So alpha is the inverse tangent of radical 3 over 2. You can punch it in a calculator, about 40.9 degrees. Okay, I can convince you of that. Do I have time to do that? Yeah, I can do that. Okay, so this one you're in degree mode. So switch over to degrees. Okay, so on my calculator, I'm in degree mode. Okay, so I want inverse tangent of radical 3 over 2. So second function, inverse tangent of square root of 3 divided by 2. 40.89, if you can't see that too well, sorry. When I do this, sometimes it burns out your eyeballs. Okay, 40.9 degrees. That is alpha. What's theta in standard position? Well, 180 minus that, right? You know this is 180. Raise it up. So theta is 180 minus 40.9. So 139.1 degrees. That's 139.1 there. Degrees. Okay. So that is that. Okay, so I'm done. I'll just talk quickly about 35. I'll look at the chat and then we'll break. 35, a woman walks due west on the deck of a ship at 3 miles per hour. The ship is moving north at 22 miles an hour. So it's almost the same thing as this one, right? You just have two components. One where she's going west at 3 miles an hour and the ship is going north at 22 miles per hour. Find the speed and direction of the woman relative to the surface of the water. So just do the same thing, right? So 3 miles per hour, have a vector going 3 left and 22 up, as it were. Okay, so that is that. Let me quickly check the chat. Okay, I know some of you just joined the row. Get that. The turning on the homework, yes, again, only those that are trying to add the class. If you're already in the class, that doesn't apply to you. Everyone trying to add, keep doing the homework. So for now, it's definitely 12.2.
I was a bit confused on where I should submit the homework. I'm trying to add and I already did today's homework, but I didn't send it because I wasn't quite sure where to send it.
Yeah,
should I just like email you?
Send it to my email address, mhum@ccsf.edu.
All right.
Okay. Get that to you just in case. I got it in the syllabus, but okay, I'm typing it here. I think you can all see that. Okay, so everything goes to mhum@ccsf.edu. Okay, you submit homework there, quizzes there, exams there, and so on. Okay, let's see. Okay, I think I got everything that we have here. Yeah, I understand some of you have connection issues. I do also. So don't worry about it, is the best way I can say it. So if you end up dropping out because of connection, you can always try to go back in. And I think we're still going to be okay. All right, so I think we're going to break. So let me stop the share. Again, we're still recording. So if you're looking at the video that you have like 10 minutes of nothing. Okay, it's 7:02. Let's start up again about 7:15-ish. Okay, so 7:15, we'll start up again. All right, and I'm going to disappear too also. Okay, 7:15, please. Okay, folks, we're gonna pick up. So I'm gonna continue on with 12.3. I've done everything I need to for 12.2. Okay, so let me start sharing the screen again. Turn off the chat. Okay, we're still recording. All right, so on the original schedule, it was 12.2 and some of 12.3. I'll pretty much keep this. I'm going to deviate when we get over here since I can kind of slow down here. So I'll give you all the formulas you need for 12.3. There's a lot, by the way. Okay, and in fact, in 12.3, there frankly are several things you may want to put on your formula sheet. It's just too hard to memorize them all. Okay. Then after a certain while, I'll stop and then we'll take our quiz. Okay. So reminder for the quiz, and some of you had me last semester. I'm doing quizzes differently this semester, so please pay attention to how I'm doing it this time. So I will project 1 or 2 or 3 questions here. You get your cell phone out and take a picture, or if you can do a screenshot, that's fine. Okay, then you get started with it. It'll take me 15, 20, 30 seconds to set up the breakout rooms, and I'll put you in your breakout rooms. Okay, you put your name down on your piece of paper, just write your name, write down the names of everybody else in your group, and then you work the problems out, and your object is to get everybody in your group to get the same answers and hopefully all correct. Okay, when you're done, the time that you have to finish by is the end of class, which is 8:25. You should finish way before that. And by the way, if you finish early, then you can all leave. And then you have until, let's say 5 minutes, so 8:30. You have until 8:30 to submit to mhom@ccsf.edu. I put it in the chat. Okay, everything you submit to me at mhom@ccsf.edu. Quizzes, your homework, your tests, they all go there. Okay, your object is to get everybody to write the same thing and correctly. Okay, I will look at everybody's individual quizzes to make sure, you know, just don't have one person send it to everybody. So I look at all 4 people. Hey, it looks like it's the same person. You know, what's going on here, right? So you have to have it in your own writing, but you definitely want to get everybody to write the same thing. Then I will grade just one person from your breakout rooms group, and you're all going to get the same grade. Okay, so since you don't know who I'm going to pick, the safest thing to do is to have all 3 or 4 people in your group have the same thing. Then, of course, it doesn't matter. Then you're going to get full credit no matter who I decide to pick. Okay, and if you finish early, you can just leave. Yeah, I'm guessing that you're going to finish early for this one. It's fairly straightforward, I think. Okay, so that's the way I'm doing quizzes now. I do see some of you put stuff in the chat, so let me see. Submit a JPEG, PDF, anything as long as I can read it. Okay, all I know is that if you take a picture and send it to me, I should be able to get it. If I can't get it, I'll let you know. Nothing too fancy. Okay, this is a school computer, and sometimes I can't get fancy stuff. So if you try to send some fancy technique, don't do it. Okay. JPEG, I think I can get. PDFs, I definitely can get. Unless if you do something funny like, I don't know, try to compress it or zip it and then unzip it, sometimes that doesn't work. So yeah. So yeah, they're due the same day. They're due at 8:25. Okay. Is a quiz on the last lecture's material? It could be, it could not be. Okay. Frankly, it doesn't really matter because it's open book, open note, open discussion. Okay. Do you need to turn in the homework? No, only those people that are trying to add had to turn in their homework, as we said before, right? So if you're already in the class, you don't have to worry about that. Okay. And my computer is kind of freaking out now a little, but hopefully it'll last. Okay, so I think I took care of that. So I'm going to go ahead and get started. So let me turn off the chat. You can still put stuff in the chat, but I won't be able to read it until I, get to it. So back to share the screen. Okay, so section 3. Topic is the dot product, page 807. the dot product applies to either a 2-dimensional or 3-dimensional vector. It's easiest to think of the 3-dimensional vector. So yeah, if you're going to put something on your cheat sheet, use the 3-dimensional flavor, and then for the 2-dimensional, just take off the K component. Okay, so a definition. If A is the vector A1, A2, A3, B is B1, B2, B3, the dot product written as A dot B, it almost looks like a multiplication symbol, okay? Only these are vectors. So by definition, it's the product of A1 and B1 plus the product of A2 and B2 plus the product of A3 and B3. So you multiply the X components, Y components, Z components, add them all up. And of course, the 2-dimensional flavor, well, you just dropped this last one. So it's A1, B1 plus A2, B2, right? A dot B. Multiply the X components, Y components, Z components, add them up. Or you could say I components, J components, K components, right? Very simple example. If you look at the 3-dimensional one there, -174 right in the middle. Sorry, I can't point to it. I don't have a third appendage. I'm using both hands to hold up the book. But -174.62 -1/2. So you go -1 times 6 plus 7 times 2 plus 4 times -1/2. So the answer is 6. And in IJK notation, look below. Okay. Well, you can make it 1, 2, -3, right? Dot 0, 2, -1, right? There's no I component. So there we go. Okay, please notice the answer that you get is a scalar. It's a number. Okay, so you have a vector dot product with another vector. The answer is not a vector though. The answer is a scalar. It's a real number. Okay, so to have a dot product, it's a vector dot another vector, but the thing that comes back out is a real number, 6, 7, or whatever. Okay, they give you a lot of properties of the dot product. You can look at it or not. You have to memorize it? Not really. Okay, some curious ones that I think you already know. A dot B is equal to B dot A. That's easy. Commutative property, right? Just switch them around. Okay, this one's interesting. Do you have to memorize it? No, you can just do it. That's what it comes out to be. That looks like a distributive law. Okay, remember when you write it like that, non-bold C means it's a scalar. Bold means it's a vector. So here are different flavors of it. You don't have to memorize it, I would say. 0 vector dot A vector is 0 number. Okay, notice that this 0 is bold, this one's not bold. That's pretty easy to show. What are the components of the 0 vector? In 3D, it's 0, 0, 0. Well, we're going to do the dot product. It's going to be 0 times something plus 0 times something plus 0 times something. It's still going to be 0, the number 0. Okay. All right, so first obvious question, what's so good about having this dot product stuff? Okay, so here's a big theorem. If you want to put this in your cheat sheet, you may. Okay. Find the angle between two vectors. This is very, very useful, especially when you're in 3D. Okay, if you're in 2 dimensions, okay, I can kind of figure it out, right? Because I can look at the paper. What if you're in 3D, right? You got one vector like this, one vector like that. How do you figure out the angle between them if they're in space, right? So it's very nice to have this formula. Okay, the angle between the vectors A and B, follow this property. A dot B is norm of A, norm of B, cosine of theta. Here's the proof. I'm not going to go over the proof. You can look at it or not. I'm not holding you responsible for the proof, but if you really got to know the proof, here it is. It's based on the law of cosines. Okay, this is true, but sometimes a more useful form is if you divide both sides by norm A, norm B, and what's norm? Norm is length or magnitude. Then you isolated cosine theta. So you can put this, but something more useful, which is equivalent, is this one. Okay, so page 809. Put it on your cheat sheet if you wish, unless you want to memorize it. Cosine theta is A dot B over norm A, norm B. One of the reasons why I like saying norm is it's shorter than saying magnitude, that's 3 syllables. And length, I know length is 1 syllable, but to me it's kind of like 1.5, because you got to say length, right? But norm kind of flows pretty easy. So how do you find the angle between the two vectors? The cosine of the angle is the dot product divided by magnitude of A, magnitude of B. And then to find theta, you just do inverse cosine, right? And I'll show you some examples of that. Okay, sorry, I got to put the book down, it's heavy. Okay, a direct result of that. Okay, do you remember from algebra, when is a fraction equal to 0? A fraction is equal to 0 when the top is 0, right? So this expression is 0 when the numerator is 0, agreed? So let's pretend the numerator is 0, 0 divided by whatever is 0. Cosine of what angle is 0 from trig? 90 degrees. If two angles are at 90 degrees, they're perpendicular. So we have a nice result of that. Again, you can either memorize it or put it on your cheat sheet. Okay, now there's a fancy word, orthogonal. I'll use it just because it's there. So what's this orthogonal stuff? It's the same thing as perpendicular. Yeah, I know you might say, why don't you just say perpendicular? I know what that means, 90 degrees. Well, they want you to get used to another word. Okay, I guess one way of saying it, the higher up in math you get, the more they're going to say orthogonal, and then less they say perpendicular. Why? I don't know why. I guess they want to make you sound more sophisticated or something. I don't know. Okay, so if you hear the word orthogonal, it's perpendicular. All right, so here we go. Two vectors are orthogonal, perpendicular, if and only if the dot product is 0. Okay, that's very useful, especially if you're out in space. Okay, so you have two vectors in space, one like this, or whatever. Okay, how do I know if the angle between them is 90 degrees, right? Now, if I just wrote on a piece of paper, all right, piece of paper, an angle like that and like that, so, oh yeah, 90 degrees. Okay, but what if I'm out in space? Okay, if I'm going like this or like this, so how do I know if it's 90 degrees? Okay, take their dot product. The dot product is 0, they're orthogonal. They meet at 90 degrees. Okay. All right, more stuff. A lot more stuff. Okay, now, in 2 dimensions, we talked about finding components already, right? So we saw that other problem at the end of the previous section. Right. 2 dimensions, problem 32, 33, right? Break it into X and Y components. How do you do it in 3 dimensions? I know this might be hard to see, so if you can't visualize it, that's okay, just use the formulas as it were. Okay, direction angles and direction cosines, page 810. Okay, look at figure 3. This is a first octant view. Again, we like it there. Of course, it's a lot harder if you're in some other octant, so let's start in the first octant. Okay, see vector A? It makes a certain angle with the positive x-axis, y-axis, and z-axis, right? If you take that and go like that, they call that alpha. This angle with the positive y-axis, as you might guess, is beta. And then this angle that it makes with the z-axis is gamma. Alpha, beta, gamma, first 3 letters of the Greek alphabet. It's alphabetical order. So alpha for x, beta for y, gamma for z. How do I find these angles? Well, now that we have this formula, right, cosine theta is A dot B over norm A, norm B. So here's A. What is a vector in this direction? I, right? So it's like saying, what's the angle between A and I? So by formula, cosine of alpha is A dot I over norm A, norm I. Okay. But what's the norm of I? What's the magnitude of I? 1. Okay. Now, A is A1, A2, A3. the vector I is 1, 0, 0. So if it's 1, 0, 0, forget about the two zeros. Okay, so you're just going to have 1 times A1. So it's A1 over norm A. Similarly, cosine beta is A2 over norm A. Cosine, sorry, this book is getting heavy. Cosine gamma is A3 over magnitude of A. Okay. Now, if you're sitting there and saying, I have absolutely no idea what you just did, okay, some of you might. If not, that's okay. Just be able to use the formulas. Okay, and just trust me on that. Okay, the angle for these vectors is such that the cosine of alpha is A1 over norm A, cosine of beta is A2 over norm A, cosine gamma is A3 over norm A. Okay, you have an interesting Pythagorean relation. We hardly ever use it. Okay, so I would say don't even put it down, but it's interesting. Cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. Okay, that kind of looks like cosine squared theta plus sine squared theta equals 1. In 3D, they're all cosines, and it looks like this. So anyway. Okay, so we have a vector in space now. Okay, how do you find the direction angles? By this. Cosine alpha is that, cosine beta is that, cosine gamma is that. Put it on your cheat sheet if you wish. Okay, now this might be a more useful way of doing it. The vector A can be written as magnitude of A cosine alpha, magnitude of A cosine beta, magnitude of A cosine gamma. You notice I said magnitude. It gets very hard when you have to say it a lot. So that's why I say length or norm. Okay, so norm A, cosine alpha, cosine beta, cosine gamma. Okay, so here's another useful formula. A divided by norm of A, that's a unit vector. Okay, so the direction cosines are the components of the unit vector in the direction of A. That's very useful. So you take the vector A, divided by its magnitude, that gives you a unit vector. What are the components? Cosine alpha, cosine beta, cosine gamma. So the gamma is the angle that that vector makes with the positive x-axis. Beta is the angle that it makes with the positive y-axis. Gamma is the angle that it makes with the positive z-axis, going back to this picture over here. Okay. All right, and more formulas, sorry. Okay. So you have a choice. You want to memorize it or put it on your cheat sheet. If I were you, I'd say put it on your cheat sheet. Okay. Projections. Okay. Projection of a vector onto another vector. Okay. Now, when we had this picture, let's look at 32. The component in the x direction, you can think of it as the projection of the vector on the x-axis. So in other words, if you shine a light straight down over here, the component would be like this, right? And for the y component, if you project a light directly here, then all you would see is this, right? Okay, so the x component is the projection of this vector onto the x-axis. So shine a light straight down, all you would see is this, correct? The projection in the y direction, so you project over here, all you would see, or the shadow you would see, is just this, right? Well, what if you want to project in any direction? Like this, a crooked direction. Okay, I guess you can kind of turn the paper and be what you have. Okay, so they go over the computation of that, okay, to get the projection. Now, there's two kinds of projections. Scalar projection, that means all I'm interested in is in the number, the magnitude. Okay, what's the length of this? Scalar projection. Vector projection is, okay, I don't want only the magnitude, I want this vector. What is this as a vector? Okay, so in this picture, it's going at an odd angle. Okay, pretend you're projecting straight down in a perpendicular fashion onto vector PS, right? If you want the scalar projection, you're just saying, what's the length of that? 5, 12, whatever. Vector projection, give me this as a vector. Okay, so that's what's going on. How does it come out to be? And here's how they write it. Whoops, sorry, the book is falling off my table. Scalar projection of B onto A. Vector projection of B onto A. Okay, B onto A is not the same as A onto B. Okay, so you have to watch out. B onto A, so you're projecting like so. If it's A onto B, it's going at a different angle, right? So for scalar projection, we use comp. Vector projection, we say proj, P-R-O-J. You raise it up. And it looks like a little subscript. See, comp A, B, proj A, B. You say, I don't want to memorize it, then put it on your formula sheet. Okay, so scalar projection is A dot B over norm A. If you do a bit of a trig, okay, and work some of this out, that's what you get. I won't go over that, okay, but it's A dot B over norm A. Vector projection, well, you take this answer, notice this is the same as that. How do I change it into a vector? You multiply it by a vector divided by its norm. Then I have the same magnitude, but at least I got the direction. Okay, and so you see A dot B over norm A squared times the vector A, all that stuff. And I'll show you examples of all this, maybe not today, but hopefully next time. Okay, it's just computation, folks. So you say, I have absolutely no idea how you derived that, how you got it. Don't worry about it. Okay, just plug it all in. Okay, but the concept is a projection of one vector onto another, not just in the nice directions, in the positive X direction, positive Y direction, but some other direction. And by the way, don't forget this might be in space. So maybe I got two vectors in space like this, right? And I want to project this one onto this one, right? So how do I do that? Just plug it in here. Okay, so again, put that in your cheat sheet for sure. Scalar projection, comp sub A, B. Vector projection, proj sub A, B. So the computation is not that hard, I would say. Okay, and you can read the proof or not. I'll leave it up to you. Okay. All right, I will get started with some problems, and then after a while, stop and give you the quiz. Okay, so where are we? 12.3. 3 to 29 odd. Okay, find the dot product. Okay, I'm actually going to choose to do number 4 just because it's three-dimensional. Yes, I know you didn't have to do number 4, but it's three-dimensional. The ones before that were two-dimensional. So I'll do number 4 for you. A dot B, 6 negative 2, 3 dot 2, 5 negative 1. So just multiply X component, 6 times 2 is 12. Y components, negative 2 times 5 is negative 10. And Z components, 3 times negative 1 is negative 3. Add them all up, negative 1. Very easy. Okay, 7. 2i plus j, I minus j plus k. I like it without the ij. I like the angle braces. And make sure it's angle braces, not parentheses, not brackets. We know that means something different, right? So the brackets, as it were, there, the angle bracket. So 2i plus j is 210, right? I minus j plus k is 1 negative 1, 1. Okay, so A dot B, 2 times 1 is 2. 1 times negative 1 is negative 1. 0 times anything is 0. Answer is 1. That's all. Okay, number 9. Norm of A is 7, norm of B is 4. The angle between A and B is 30. Find a dot product. So I'm going to use this guy. A dot B is norm A, norm B, cosine theta. So again, when I say norm, N-O-R-M, that's another word for magnitude or length. Okay, so they told me norm A is 7, norm B is 4, theta is 30. So A dot B is norm of A, norm of B, cosine 30 degrees. Just plug it in. So 7 times 4, cosine of 30 degrees is radical 3 over 2, 14 radical 3. Okay. All right. A little bit harder, I suppose. 11. U is a unit vector. Find U dot V, U dot W. They give me an equilateral triangle. That means they're all 1. U, V, and W are all length 1. And the angle is 60 degrees. But notice the arrows. U is going left and down. V is left and down. W looks like it's going to the right. Okay. So I got the picture here. Okay, now the key thing about this is when you're doing a dot product of two vectors have to start at the same point. They have to emanate from the same point. Okay. Now, U and V already emanate from the same point. Okay. So U dot V by formula is norm U, norm V, cosine of the angle between them, which is 60 degrees. Okay. Well, they told us that these are both unit vectors. So that's 1, that's 1. Cosine of 60 degrees is a half. So the answer is 1/2. What's a little bit trickier is they say U dot W. Okay. In order to get U dot W, U and W both have to emanate from the same point. They got to start at the same location. So that means I have to pick up U and bring it down here so that U is coming down like so, and W is to the right, which means the angle right here now becomes 120 degrees. Right. So that's what I got to do, because that's 60 degrees. So that's one's a little bit tricky. To find U dot W, you can't use 60 degrees. You move U down in here so that they both start from the same point. So the angle between them is 120 degrees. Okay, so U dot W is norm U, norm W, cosine of 120, which is 1 times negative a half. So the answer is negative a half. Okay, so that one was a little bit trickier. Okay. Okay, let's see. 13, show and tell. Show that I dot J equals J dot K equals K dot I, which is 0. And show that I dot I, J dot K, and K dot K are all 1. Okay? You pretty much just do it. Okay, it's not hard at all. Okay, so I'll show you one of each. I'll do you one from A and one from B. So J dot K. Well, J is 0, 1, 0. K is 0, 0, 1. Take the dot product. 0 times 0 is 0. 1 times 0 is 0. 0 times 1 is 0. 0. Okay. Which incidentally means we had that theorem. That means they meet at 90 degrees. And we already know that, right? The vectors I, J, and K are all at 90 degrees. Okay. I'm not sure if I can do this very well. Okay, but I, J, and K are sort of like this. I can turn this a little so you can see it. But you've probably seen models like this, especially you physics people. Okay, they all meet at 90 degrees. K dot K. K dot K, what is K? 0, 0, 1. Dot 0, 0, 1. 0 times 0 is 0. 0 times 0 is 0. 1 times 1 is 1. You get 1. Okay, pretty straightforward, I think. All right, then let's see. Find the angle between two vectors. Find an exact expression and then the approximate to the nearest degree. So 15 is 2-dimensional. 17 and 19 are 3-dimensional. So I'll do the three-dimensional flavor for you. Okay. So how about I do 17? Okay. So you have the space vectors now. You're in space. 1, -4, 1, 0, 2, -2. So imagine, okay, you've got two vectors in space. How do you find the angle between them? So here we go. So here's A, here's B. So I use the formula cosine theta is A dot B over norm A, norm B. So dot product, 1 times 0 is 0, -4 times 2 is -8, 1 times -2 is -2. So the numerator is -10. How about the bottom? Magnitude of A, square root of 1 squared plus -4 squared plus 1 squared. 1 plus 16 plus 1. Magnitude of B, 0, 2, -2. Square root, 0 plus 4 plus 4. 0 squared plus 2 squared plus -2 squared. So -10 over radical 18, radical 8. 18 times 8 very conveniently is 144, whose square root is 12. So -10/12, which reduces to -5/5. So cosine of the angle between them is -5/5. That's cosine theta. How do you get theta? Inverse cosine, right? So the exact expression is inverse cosine of -5/5. Punch it in the machine, 146 degrees to the nearest angle. And that's what you got. Okay. Okay, so I think I'll stop with 21. What time is it? 55. Okay, you still should have at least half an hour to do the quiz. 21. Find correct to the nearest degree the three angles of the triangle with the given vertices. So 21, 2, 0, 0, 3, and 3, 4. And I'll stop there. Okay, so for those of you trying to add the class, let's say up to 21. Okay, so do the homework from 12.2 and 12.3 up to 21 for people that are trying to add. Again, if you're already in a class, that doesn't apply to you. Okay, so submit it by Tuesday. Oh, by the way, one big advantage for, I might be able to work it out before then. So if you want to submit your homework early, for those of you trying to add, I might be able to give you an add code earlier also. So technically it's due Tuesday, but if you want to submit it earlier, okay, I'll look at your priority. I have your priority on the original wait list that I got from City College, okay? For some of you are higher priority than others, okay? So if you want to submit your homework earlier, I might be able to give you your add code and add you to the class earlier the next Tuesday. Something to think about. Okay, so again, so section 2 and up to problem 21 for section 3. Again, only for those of you trying to add still. Okay, so 200334 for problem 21. Okay, so here's the picture. 200334. And if you're like me, we're a lot more comfortable in 2D, right? So, oh yeah, I can see that. I know what the angle is. But once you move to 3 dimensions, right? Once I go into space, then it's a little bit harder to visualize, visualize a triangle in space, right? Where they're all over the place, perhaps. Okay, so find angles P, Q, and R. I'm only going to do one of them. The others are completely analogous. Okay, so find the angle P. So first, find the vector PQ and the vector PR. Here they are, -2, 3, 1, 4. So from P to Q, delta X is -2, 0 minus 2. Delta Y is 3, 3 minus 0 is 3. From P to R, delta X is 1, delta Y is 4. Okay, I'm going from P to R, so it's 3 minus 2, which is 1, 4 minus 0. Okay, so I use the formula cosine of P is the dot product over magnitude of PQ, magnitude of PR. Okay, so dot product of these two guys, -2 times 1 is -2, 3 times 4 is 12, 10. magnitude of PQ, square root of -2 squared, 4, 3 squared, 9. Norm of PR, square root of 1 squared, 1, plus 4 squared, 16. So 10 over radical 13, radical 17. Okay, 13 times 17 comes out to be 221. If you can't read that, 221. So 10 over radical 221. All right, so P is the inverse cosine of 10 over radical 221. Answer is 48 degrees. So there we are. And do the exact same thing for the other angles. Although, I guess when you stop and think about it, you only have to do one more, right? Once you find a second angle, you can just use the fact that the sum of the angles of any triangle is 180 degrees. Okay, but I mean, maybe just for practice, do the third one anyway and see if it does add up to 180, right? But we already got angle P, 48 degrees. So let's say you figure out angle Q, then you can just go 180 minus the sum of these, and that'll do it, right? Okay, so I will stop at problem number 21, and I will now give you the quiz. Okay, let me check the chat. So yeah, quiz is due today. Now, let's see. When the numerator is 0, okay, I think you mean when the numerator is 0, that means the dot product is 0. Okay, you had a fraction. The formula looks like this, so I think this is what you mean. You have this, right? If the dot product is 0, numerator is 0, 0 divided by anything else is 0. That means the angle is 90 degrees. That means the two vectors are orthogonal or perpendicular. Okay. All right. Yeah, I see a lot of you who had me before are kind of questioning about that. So I'll give you the quiz. It's due technically when class is over at 8:25. When I shut the session out, you have 5 minutes to, take a picture, get your cell phone, click, 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 and email me at mhum@ccsf.edu. Okay. All right. So get your cell phones out. Okay. And again, the way it's going to work is I'll show it to you. Go ahead and get started. I will set your breakout rooms. Okay. On your piece of paper, put down your name, everybody else in your breakout group's name. You'll be in a group of either 3 or 4. Okay. It's up to you if you want to turn your camera on or not. It's just to me, if no one's, it's like everybody's like this, right? You can't see anybody. Okay. Although I've had other classes, you might want to go like that just to show somebody the work. Okay. Your object is to get it right. And everybody else in your breakout room also has it right. Okay. So everybody puts the name of everybody else in your group. Okay. I will look at all of them. I'm only going to grade one of them. Okay? And you're all going to get the same grade. So obviously, the only way to be sure that it's going to work out for you is if all 3 or 4 of you have the same thing. Then, of course, it doesn't matter which one I grade. You'll get full credit. Okay. Any quick questions about that? That's the way I'm doing quizzes this time. All right. So get your cell phone cameras out. Or do a screenshot. And here we go. And unfortunately, I can't show you the whole thing at once. Okay, or maybe I can, just maybe like that. I'll also read it. The top just says Calculus 3 Quiz 1. Find the distance between the points 3, -1, 6, and 5, -2, 1. Find the distance between 3, -1, 6, and 5, -2, 1. Question 2. They give us a box. Okay, maybe I can raise that up a little bit. Okay, here's a first octant picture of a box. There are 8 corners, just like a Rubik's Cube, right? There's 8 corners on this. 2 of the corners are the origin, and 1, 2, 3. All I want you to do is give the other coordinates, A, B, C, D, E, and F. Okay, sorry, I keep moving it. You might have to take more than one picture. Okay, so here's A, here's B, here's C, D, E, and F. Just give me their coordinates. Okay, I'll hold this for another 15, 20 seconds. Go ahead and get started. Yeah. Oh, this is a pretty good picture. I'm gonna get this. Okay, if you finish early, you may leave, but make sure you get it right. Make sure all your teammates get it right. You can leave, do it 8:25, the end of class, but technically 8:30. So I'll give you 5 minutes to get your cell phone, click, 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 and then email me at mhum@ccsf.edu. Okay, I will now assume everybody has it. You've all got the picture or screenshot or whatever. Okay, so go ahead and get started. I will stop the share and set up your breakout rooms. I will stop